Biorefinery System Module 12 Lignocellulose Biorefinery Process Engineering Part 2 Segment 3 Solid-State Fermentation Bioreactor. With me, Yusuf from Bioengineering Study Program, School of Life Sciences and Technology, Institut Teknologi Bandung. We have previously discussed about steam explosion pre-treatment and equipment, as well as Carding fractionation equipment. In this segment, we will discuss about solid-state fermentation and gas double dynamic solid-state fermentation bioreactor. Solid-state fermentation plays a more important role in industrial fermentation processes compared to the traditional submerged fermentation, because it resolves the problem of solid waste disposal. Solid-state fermentation is defined as fermentation involving solids in the absence or near absence of free water. However, the substrate must contain enough moisture to support the growth and metabolism of microorganisms. It offers advantages including low energy requirement, high product concentration, and little wastewater production, and is environmental friendly compared with submerged fermentation. However, given that the substrate used in the solid-state fermentation are always agro-industrial products with low thermal conductivities, the heat removal in the solid-state fermentation process is slow. Thus, the problem of overheating in the fermentation medium has become a bottleneck of solid-state fermentation technology. In 1998, a large-scale solid-state pure culture fermentation demonstration plant was built, and the results showed that economic indicators of this technology were better than traditional submerged fermentation. On this basis, the gas double dynamic solid-state fermentation technology has gradually developed into one of the modern solid-state fermentation technologies. In the traditional solid-state fermentation process, the transfer of heat and mass were usually enhanced by mechanical agitation, in which the gas phase was fixed and the solid phase was continuously agitated, in order to mix the solid substrate particles completely and strengthen the contact between the particles and gas molecules. During the agitation of solid-state fermentation process, the growth of microbes would be damaged by the shearing force. In addition, it is difficult to seal the equipment and the energy consumption is high. The sticky wet materials also make a direct contact with fermentation tanks, which can easily cause the occurrence of dead corners in the fermenters. If the agglomeration of the medium cannot be completely avoided, the efficiency of heat and mass transfer are adversely influenced. These shortcomings of traditional solid-state fermentation can all be overcome by gas double dynamic solid-state fermentation. The transfer of mass and heat can be improved, and both the gradient of temperature on the oxygen and the carbon dioxide concentration can be reduced. At the same time, the activity phase of microbial metabolism can be promoted by periodic high-pressure pulse. The gas double dynamic solid-state fermentation consists of a horizontal solid-state fermentation cylinder, a built-in circular duct, cooling pipes, blowing devices, and an air circulation system. Gas double solid-state fermentation can be divided into two types: systems using a single vessel as shown in the left figure, and double vessels as shown in the right figure. There are several important characteristics of gas double dynamic solid-state fermentation. First, no mechanical agitation device. The transfer of mass and heat is achieved by air circulation. Second, the bioreactor structure is simple and easy to seal. Third, the fermentation tank is a pressure-resistant container which can be sterilized by steam pressure. Fourth, during the fermentation process, the pressure of the fermenter is kept positive, which is easy to keep sterile. Fifth, the microbial metabolism could be enhanced by cycle stimulation. 6. The temperature and humidity of the bioreactor are easy to control. And last but not least, the fermentation process is automated. The gas double dynamic solid-state fermentation technology is developed from three solid-state fermentation. Pressure pulsation in the gas double dynamic fermentation process is accomplished by supercharging and decompression of sterile air. One cycle of pressure pulsation consists of 4 stages: pressurization, high pressure holding, depressurization, and low pressure holding as shown in the figure. The duration of the supercharging state is long and the curve rises gently. The duration of decompression is as short as possible, generally from a few seconds to 1 minute. The duration of the high-pressure stage thermometric stage can be set freely according to different fermentation. The gas double dynamic solid-state technology has groundbreaking significance both in terms of theory and industrial applications. Based on the results of experiments and practice, the technology can be applied to a wide range of microorganisms such as bacteria, fungi, and actinomycetes. Gas double solid-state fermentation technology breaks the monopoly of submerged fermentation technology in the modern fermentation industry. Due to the unique advantages of this fermentation, a lot of liquid fermentation technology could be replaced by gas double solid-state fermentation technology, such as production of pesticides, production of cellulose, production of pectinase, and production of riboflavin. A lot of new products can be produced by gas double solid-state fermentation, and more importantly, the bioconversion of lignocellulose substrate can be achieved to produce, for example, cellulose ethanol and bioorganic fertilizer. Compared to traditional solid-state fermentation technology, fermentation times tend to be shortened by 1/3 using gas double solid-state fermentation technology. Figure at the right shows a breathing solid-state fermentation bioreactor. The whole fermentation system consists of 2 fermentation tanks. There is a reciprocating pump between the 2 fermentation tanks. The air passes from one fermenter into the other. The negative pressure tank, such as fresh air, and forms an atmospheric pressure tank. At the same time, the high pressure tank outlets exhaust gas and subsequently forms atmospheric pressure. The circulation of negative pressure, atmospheric pressure, and high pressure proceed until the end of the fermentation. Carbon dioxide could be discharged and heat could be removed by repeated cycles of breathing and sucking in the 2 parallel fermenters. For the next segment, we will discuss about online determination and automatic control. Until then, I am Yusuf from Institut Teknologi Bandung.